All right, I'm going to show you guys how to do an elevator problem now. So the elevator problem says Bob has a mass of 200 kilograms, which is a lot. Bob is a big boy. He has been told that he can lose weight by descending in an elevator. He places a bathroom scale in the elevator, stands on it, and presses the down button, causing him to descend at an acceleration of 4 meters per second squared. What does the bathroom scale read on the way down? Now, whenever they're asking for what the bathroom scale reads, what they're asking for here is the normal force. All right. Now, the normal force is, of course, the force of the ground on your body when you're standing. It's the one that's holding you up. The normal force can change. Force of gravity can't, though, okay? You know that the force of gravity is equal to mass times the acceleration of gravity, or your weight, or Bob's weight. But remember, mass is the amount of stuff your body is made of. It's not going to change. And then the acceleration of gravity on Earth is also not going to change. So your force of gravity doesn't change. But what does change and can change is the normal force. So the normal force is what a scale will read. It's how much that scale is being pressed down, basically. If you've ever had a scale in front of you and you take your hand and you press down on it, the scale reading will increase. It's because of Newton's third law. Every action has an equal and opposite reaction. You're pressing down with a certain force. The scale is pressing back with the same amount of force. That normal force is the same force that you're pressing on the scale with, and therefore it's going to increase the more you press on that scale. This is also the reason that elevators are fun to ride in, and you can feel lighter or heavier on an elevator. It's because the ground is pressing on you at different forces, which different than what you're used to. So the accelerations are exciting. It's also the same reason why if you go on Goliath at Magic Mountain and you're pressed into your seat, have you ever felt that when they're doing that corkscrew turn? You're pressed into your seat and you almost black out because you feel so heavy, your blood rushes to your feet and all that fun stuff. So really, the reason that elevators and roller coasters are exciting are because of the accelerations and how we feel with this normal force. So that was a big rant, but it's very interesting stuff. So if we draw a free body diagram of Bob, here's Bob. There he is. We know that Bob is on the Earth, so he has the force of gravity downward, and then we know that there is a normal force upward. Now remember, we are drawing the free body diagram, oh my gosh, I can speak, of Bob in this elevator, okay? And remember, the object that we're drawing the free body diagram is of Bob. It's not of the elevator. You're not going to draw tension or anything like that. Bob is standing on the floor of the elevator, which is why we have a normal force, and then he is on the Earth, so we have a force of gravity. Now, it says that we're moving downwards, so acceleration is going to be downward. So just like I did in that previous vertical acceleration problem, I'm going to draw the acceleration into my picture because I like to say that whatever direction we're going is our positive direction. Well, really, I like to say the direction of acceleration is the positive direction too. So here I'm going to say that the positive direction will be downward, and that's the direction of my acceleration. Now, we know that we are trying to solve for normal force because we want to see what the bathroom scale reads on the way down. We also know that that acceleration is equal to 4 meters per second squared. All right. Now, the thing that we don't know yet is we don't know the force of gravity, but we know that we can find it because the force of gravity is mass, Bob's mass, times the acceleration of gravity. So force of gravity on Bob is mass times acceleration of gravity. Remember, Bob's mass is 200 kilograms times the acceleration of gravity, 9.8 meters per second squared. And we get that Bob's weight, or his force of gravity, is 200 times 9.8, which is 1,960 newtons. All right. So I said that down was positive because I want to plug in a positive number for my acceleration. So because of that, that means the force of gravity is the positive force, the normal force is the negative force. So we end up getting net force is equal to mass times acceleration. Net force will be force of gravity minus the normal force is equal to mass times acceleration. Again, I know everything here except for the normal force, so that's what I'm going to be solving for. So I'm going to add normal force to both sides. We get force of gravity equals mass times acceleration plus normal force, and then I'm going to subtract mass times acceleration from both sides. So we get normal force is equal to force of gravity minus mass times acceleration. Now I can plug in my numbers here. I get that the normal force is equal to the force of gravity, which I just found to be 1,960 newtons, minus Bob's mass, which is 200 kilograms, times the acceleration 4 meters per second squared. So we get 1,960 minus the quantity 200 times 4, and we get 1,160 newtons. So Bob does feel lighter. Because the normal force is less than the force of gravity, Bob feels lighter as he's going down in that elevator. And you've probably felt this before too. If you go into an elevator at the top floor, you press the button, you go down, you feel lighter. You might even try to jump and see if you can jump really high. Now, the reason for that is that you're standing here, right? That floor is almost falling out from under you. So since the floor is falling out from under you, it's not pressing on you as much as it usually does. So therefore, your normal force is less. Therefore, you feel lighter. Now on the bottom floor, if you get on at the bottom floor and then you press the button to go up, as this elevator starts going up, your inertia, you kind of want to stay there, right? Remember, bodies at rest, stay at rest. Inertia is a resistance to a change in motion. Your body has a resistance to a change in motion. So the elevator starts accelerating, you get pushed into the ground. Therefore, you're putting more force on the ground than you usually do. Therefore, your normal force is larger, and therefore you feel heavier on the bottom floor of that elevator right there. So the take home here is that, number one, when you're doing these vertical acceleration problems, make sure that you denote a positive direction. Now, I was allowed to denote any direction positive, really, but usually I like to say that the direction of acceleration is positive. The reason I say that is because then I plug in a positive number in my equation. I could have said that upwards was positive, but then I would have had to plug in a negative here, and then the two forces, my force of gravity and normal force, would have been different. Okay, so that is very important. Make sure that you are careful with your signs here. Now, the other thing that I want you guys to remember about this is, whenever they're asking for what the bathroom scale reads or how heavy or light someone or something feels, they're asking for that normal force, because the normal force is how you feel. It's how much you're being pressed into the ground. It might be lighter sometimes, and that's why we feel lighter. It might be heavier or more sometimes, so that's why we feel heavier. So this is why we feel different ways in an elevator or on a roller coaster or something like that, and why those things can be exciting.